I have another separable differential equations problem for you. So here's what it says. It says find the family of curves where the points along these curves have a derivative value twice the slope of a ray from the origin to these points. So again, we're describing to you a situation of some curves here, and what you want to do is probably sketch out what's going on here and try to set up a separable differential equation and solve it. So knowing that, why don't you pause the video and work on this problem here and see what you find. All right, assuming that you've given it a go, again, let's try to visualize what's going on here. So we're looking for a bunch of curves with this description here. So let's see, if we were to drop down some axes, we'd have something like this. This could be X and this could be Y. And then we're looking for a bunch of curves. So we got some curves going on here. Maybe it's something more. There we go. Something like that. Okay. And then we have a ray coming to a point along this curve from the origin. We have a ray coming from the origin to a point on this curve. And maybe we can call this point, let's call this point XY. Let's call this point XY. All right. And again, what are we looking for? Well, this curve has to have this specification that the derivative. So if we were to make a tangent line at this point, xy along this curve, the slope of this tangent line, we're told, needs to be exactly 2 times the slope of this ray coming to this point from the origin. That's what we're looking for. So now that we've kind of visualized this, again, we can just take these words and write out a differential equation. So here's what I mean. We're told that the derivative value of these curves, so our derivative value, dy dx, needs to be what? It needs to be twice the slope of our ray from the origin of these points. So what is the slope of this ray here? What is the slope of this ray? Well, again, just dropping down, talking about slope, rise over run, so we have y over x. So 2 times y over x. And you can see this is a differential equation, and we can solve it by separation of variables. So why don't you pause the video, and now that we have this differential equation, why don't you try to find the solution to it? All right, assuming that you've given it a go. Again, with separable differential equations, we're trying to get all of our x's and dx's on one side and all of our y's and dy's on another side. We're separating them. So here we go. Let's multiply both sides by dx. And here's what we'll have on the right-hand side. We are going to have 2 times dx over x. All right. And then on this left-hand side, when we divide both sides by y, we're left with dy over y. And now all we need to do is integrate both sides. So we get something like this. And after integrating on this left-hand side, we are going to have the natural log of the absolute value of y. And then on this right-hand side, we're going to have 2 times the natural log of the absolute value of x. And then we can't forget our constant. So that's what we have after integrating. And maybe just a quick note on why we're keeping absolute values here. These truly are the antiderivatives of when we antidifferentiate 1 over y. This is what we get. And in other problems, sometimes we know that we're only going to have positive y or positive x values, and we can lose this absolute value sign. But in this case here, we're looking for all the curves. So there's no sort of thing told to us in these instructions here, or problem statement that tells us that y and x can only be positive. There's nothing in here that says that. So we are, again, dealing with the absolute value of both of these. And now we want to explicitly solve for y. So we can do that through exponentiating both sides. So we have e to the natural log of the absolute value of y is equal to e to the 2 times the natural log of the absolute value of x plus c. And now on this left-hand side, we again are left with the absolute value of y. And then on this right-hand side, let me just rewrite this a little bit. I don't want us to get lost in some exponent and log rules here. So we can actually rewrite this as e to the natural log of the absolute value of x, and all of this is going to be squared. All right, and then we're left with e to the c. So like in other problems, we're going to let e to the c power be equal to this capital A, And then we're going to get the following. So we again still have this absolute value of y, and that is going to be now equal to a times the absolute value of x squared. And really, this is redundant. This absolute value sign is now redundant because if we have a negative value here, when we square a negative value, we're just going to end up with a positive value anyway. So we can get rid of that. So we have the absolute value of y is equal to a times x squared. And this is our solution here. And really, all right, we're allowing both y to be both positive and negative. So we're going to get the following. On one hand, we're going to get y is equal to ax squared. And then on the other hand, we are also going to get y is equal to negative ax squared. And what are both of these here? Because these are our solutions right here. These are our solutions. What are these here? These are a collection of parabolas that have a vertex at the origin, and that is going to be pretty cool. So what I did was graph out this solution beforehand, and this is what they look like. So we get the following. We get all these parabolas with vertexes at the origin. And this is our solution here. And what is that saying? Well, in regards to our problem, when we take a ray, this is saying that when we take a ray from the origin to any point along these parabolas here, when we make a tangent line at this point here, the slope of this tangent line is exactly twice the slope of this ray coming from the origin to that point. And you can do that for any point along these parabolas. They all have that condition, which is pretty cool. And another thing that we can do, again, with separable differential equations, when we get some solutions to differential equations, we can check those solutions by differentiating them. So let's just check that these solutions are good. So let's differentiate our positive, our upward facing parabolas. So we get dy dx is equal to 2ax, and I'm going to rewrite it as 2ax squared and then over x. And now you can see we can substitute ax squared in for y. So we're left with 2 times y over x. And that's equal to dy dx. And that's exactly what we started out with. If we were to scroll back up, that's exactly what we started out with. So that solution works. We just proved that. And now let's check our downward facing parabolas. So we have differentiating them. We have dy dx is equal to negative 2 times ax. And again, I'm just going to rewrite these. So this is negative 2 times ax squared over x. And then we can substitute in for y again. So we are left with 2 times y over x. So we have just proven that both of our solutions are valid. And again, we get this solution set, which is pretty cool. But before we go, I want to ask a few questions. There's a few things that we need to clean up here. Number one, what about the solution y is equal to 0? What about the solution y is equal to 0? Is that a valid solution to what we were described? Would that be a valid solution? Well, the answer is yes, but it's not contained in our solutions down here. So what I'm saying is, all right, this line here, y is equal to 0, is a solution. If you were to take a ray to any point, if you were to take a ray from the origin to any point along this line here, y is equal to 0, both, if you were to make a tangent line and figure out the slope of that tangent line here, it would have a slope of 0, and the slope of this ray here would also have a slope of 0. So 0 times 2, yeah, that's still 0. So this is a valid solution. But you can notice when we look at our parabolas down here, can our capital A, if A is equal to e to the c power, is there any sort of c value that would make capital A 0? The answer is no. Their answer is no. So down here, we're saying that A can only be positive and A can only be negative, but it can never be 0. But up here, we just proved that y can be equal to 0. So what's going on here? Why wasn't that picked up in our solutions? Well, it wasn't picked up in our solutions because we divided by y. So that we lost that, because again, if y is 0 over here, we're undefined. But we can see through looking at this graphically that this is a solution. It just wasn't picked up because we divided by y. So that's one small point. Another small point. Again, I don't want us to get confused in these subtleties here. Another point that we can make is asking ourselves, what about the origin? So if I were to erase some of this, you can see that when I plotted our solutions here, I left the origin undefined. And why is that? Well, looking at our separable differential equation that we had up here, our differential equation, we can see that when x is equal to 0, we're undefined. We're undefined. And if you were to plug x back in to our solution set, we would get the origin. So at the origin, we are indeed undefined. But yet, looking at our parabolas, it's saying that these parabolas have vertices at the origin, that we are going through the origin. That's what these solutions are saying. But yet, our differential equation is saying we can't go through the origin. It's undefined there. So what's going on? Well, what's happening is, again, this is a little beyond this class here, and I won't say too much on it, is that since our differential equation says that we're undefined at x is equal to 0, and that turns out to correspond to the origin, that any sort of solution that we have on these parabolas here does not have to obey any sort of rule across the origin. So if we come on this branch of this parabola here, we can leave on a separate branch. There's no rules that occur to our solutions across the origin. So again, that's a small, subtle point, and again, it's kind of beyond the scope of this class. What I want you to take away is that we found these solutions here of all of these parabolas, this collection of parabolas, and the solution y is equal to 0. That's the solution to this problem, and it was cool because we weren't told a differential equation to solve. We had to construct our own based off of a geometric description. And in the next video, we're going to use this solution that we found in order to solve another problem.